Now, these images, then the top one is the Bragg's law. And this is estimated that the incident ray comes and it is diffracted to 2 theta angle and you get that. Here again, it is just to show that this is happening. And here is the single crystal, right? And along the circumference, you are carrying the detector and taking measurements from different directions, right? And here you will get a pattern, and that pattern will give you rings or strips, and those distance between rings will tell you about the interplanar spacing. And other interesting thing which I told you in the last lecture as well, but we are talking about X-rays, then you can understand it now that if you have a diffraction pattern like this and the electron diffraction, it is a diffused ring. A diffused ring. Diffused ring is a representative of glass. Amorphous. If you have a diffraction pattern like this, then as I told you in the spotty diffraction pattern, that you are having A, R1, R2, R3, R4, these are all the reciprocal lattice vectors. Here, this is R1, this is R2, R3, R4, and interplanar spaces are these, right? These are the interplanar spaces, but it will give you R, and you will convert it into these spacings. Now, this diffraction pattern, look at the geometry and symmetry. This is diffuse ring, and in XRD, you have an amorphous hump, right? Here, for large crystals, you have sharp peaks and you have spots in the electron diffraction pattern. Here, you have rings in the electron diffraction pattern, and in the X-ray, you have broader peaks. So when you look into the diffraction pattern of a material, you should be able to know what sort of material it is. Is it a nanomaterial? Is it a microcrystalline material? Or is it amorphous? So from just a look at the diffraction pattern, you know about the nature of the material. Bragg's law. Diffraction from a three-dimensional periodic structure such as atoms in a crystals is called Bragg's diffraction. I have forgotten comma S. It is similar to what occurs when waves are scattered from a diffraction grating, right? When waves are scattered from a diffraction grating, in the same way, the Bragg's law is doing. Bragg's diffraction is a consequence of interference between waves reflecting from different crystal planes, and the condition for constructive interference is n lambda is equal to 2d sine theta. Lambda is the wavelength of the incident radiation. Remember this, when you write your thesis, your paper, you must explain each and everything upon first use. You will have to write lambda is the wavelength of incident radiation. and its value is 1.54 something angstrom for copper, if you have used copper source. If you have used another source, then its wavelength will be different. D is the interplanar spacing, theta is the angle of the diffracted wave. But we are saying 2 theta, right? So it is the angle between the incident and the diffracted is 2 theta, but the angle of the plane in the diffracted beam is, this is the plane and this is the diffracted beam. So this angle is theta. When this angle of incident is added here, then the angle between these two becomes 2 theta. Right? And m is an integer known as the order of the diffracted beam. Some people write it m, some people write it n. Yes. But always write the most conventional form, because there are many people who mind this, who doesn't understand that it is a symbol simply. It has nothing to do with m and n. But when you see it means an integer, so whether it is p, m or n, it makes no difference. But use the conventional symbols. It is important for science, because many people understand that. They are common. So, Bragg's law of diffraction, when a collimated beam of X-rays is made incident upon a pair of planes, lattice planes in a crystal, each atom acts as a scattering center. Now look into this. Each atom acts as a scattering center, because you may be thinking that from where does the diffracted beam come? So each atom is behaving as a scattering center and emits a secondary wave. All these secondary waves interfere with one another to produce the diffracted beam. Bragg's approach was very simple. Consider crystal as parallel planes of atoms, distance d apart. Listen to this carefully so that you don't confuse when you hear about X-ray. Right? It is very simple thing. Then assume mirror-like reflections of X-ray from any given plane. When rays scattered from successive planes interfere constructively, peaks of scattered radiation will occur. Successive planes. If the successive planes are equidistant, if the successive planes are equidistant, then there will be periodicity. And when there will be periodicity, there will be Bragg condition will be satisfied. If they are not equidistant, then obviously the scattered waves path difference will not be integral multiple of the wavelength lambda. And if they are not integral multiple of wavelength lambda, then the Bragg condition will not be satisfied and no diffraction will occur. Here, incident beam goes up to n and diffracted from there, making an angle theta of incident with the sample and angle theta of scattering with the plane. Now, when this beam is coming here, and when it reaches here, it travels how much distance? this much, say PO and OQ. PO and OQ. PO and OQ. Right? When this wave reaches here to become parallel with the other diaphragmatic beam, it travels an extra distance. Similarly, if a plane is here and another beam is coming here, again, if that PQ, PO plus OQ is this place is D sine theta. If this is a triangle and this is the angle, then this is D sine theta, D is this here, and this is D sine theta, right? So you add these two, D sine theta plus D sine theta is equal to 2D sine theta. If this path difference carefully located is, it goes up to there and goes there. It goes there and then travels this extra distance. Similarly, for the next plane, it will travel another extra distance. So if this extra distance is integral multiple of n lambda, then Bragg's diffraction will occur and you will see a crystal there. So a peak will be there. Now, the directions of the reflected beam, diffracted beam, depend on the geometry of the lattice. That is, on the orientation and spacing of the crystal planes. The orientation and the spacing between the crystal plane. If for a crystal of cubic symmetry, we are given the size of the unit cell A, the angle at which the beam is diffracted from the crystal plane, HKL, can easily be calculated from the interplanar spacing, because D, A, and HKL under root. So HKL, you put the values, you know A, and you can determine from there the interplanar spacing, right? But 2D sine theta is equal to n lambda DHKL. This D is DHKL. We are moving a little bit forward now. D is not simple D now. D is DHKL, and HKL are the Miller indices of that plane, about whose spacing we are talking. So now the parallel planes will be 100, 200, 300, 400, 500. All are parallel planes, and their interplanar spacing is DHKL. DHKL in that case which I told you will be D100, D200, D300. But the orientation of the plane 110 will be different than that. The orientation of the plane 110 will be different than the plane orientation of the 100. And that is why they are saying that the direction of the refracted beam depends upon the orientation as well as the interplanar spacing of that particular crystal plane, right? And here you can measure where n, capital N, let us do it. Lambda is equal to 2a. D100 is A. So don't confuse with that. D001 is C. D1010 is B. Right? So don't confuse with these things. So D scale is equal to n lambda over 2 sine theta. You have taken D out, and lambda is equal to 2a sine theta. So when you know A, when you know theta, so you can measure lambda as well from there. Right? And n is n square h square plus n square k square plus n square h square. I am taking you towards a classical method in a short time, that what people used to do here, where n is the reflection or line number. This is the number. Right? 1, 2, 3, the order of refraction when you move forward. For second order, from 100 planes n is equal to 2. Right? That is H1, K0 and L0. This reflection may be referred to either as the 200 reflection or as line 4. So all the parallel planes have the same H-scale indices. It depends upon your own choice of the origin. If this is a crystal of these planes, then your origin is here. These are planes. If your origin is here, then this is your 100. If your origin is here, then this is your 100, and this will become minus 100, and the top one will be 200. So it's upon you where you choose the origin. But when you are doing this in the electron diffraction, the next plane in order of decreased spacing will be 110. How will be 110? This is 100. And this is say 010. Then this is 110. Right? The vector addition of these two gives you 110. And it is nearer than this and this, because, can you tell me why? This plane is nearer than this and this? Is this nearer than this and this? Is it? Why? We are talking in the reciprocal space. When the distances are large, this means these planes are nearer in the real crystal. Right? So that is why people don't call it D-spacing. People call it R-spacing. Reciprocal lattice vector, R1, R2, R3. And D is inversely proportional to R. Right? So that plane will become nearer. The next decreased spacing. Decreased spacing means nearer. Right? Will be 100 planes, 100 planes. he has used the middle bracket. He has used the middle bracket. Why? Because if he was telling us the 110 plane, then there should be the small parenthesis. But he is putting like this. What does this mean? When he is talking of all the parallel planes of the type 110, 220, 330. So when you are representing a group of planes, then you use that side of symbolism in your presentation, for which D110 will be equal to A over under root 2, while a dihedral 110 plane will have a spacing of 111 plane, 111, 1 H plus K plus L, it will be 3. So it will be A divided by under root 3. And when you know A, you can measure the spacings for various HKL indices. So it is not a difficult work. The angle at which any of these planes in a crystal reflect an X-ray beam of wavelength lambda may be calculated by inserting the appropriate value of D into the Brain's equation. So you can measure, if you know about D and A, you can measure theta. If you know about theta and D, you can measure A. If you know about theta and A, you can measure D. Right? So there are various experimental procedures which give you different sort of information, and you transform them accordingly to ensure that Bragg's law is satisfied and that reflection from various crystal planes can occur. It is necessary to provide a range of either lambda or theta. So both can be used. Right? Either the intensity should vary according to theta or according to lambda, and that will give you, when you put it into that equation, it will give you the other parameters. So if you know lambda, then it will give you theta. If you know theta, you can derive lambda from there. So how does it look like? This is X-ray tube. This is a slit, the working slit, sample, and scatter slit. Receiving slit. The receiving slit means to filter out the scattered radiations at larger angles. And then secondary monochromatic, then again you combine the beam, right, to go into the detector, and detector then gives you intensity at different angles. I included, when you go into the reciprocal lattice space and when you are representing things in 3 dimensions, then you go to the stereographic projections, in which you can represent 3-dimensional space on a 2-dimensional paper or plane, right? For any family of lattice planes separated by a distinct D, there are reciprocal lattice vectors perpendicular to the plane. Reciprocal lattice vectors perpendicular to the plane. arcs, reciprocal lattice vectors perpendicular to the plane, the shortest of which has a length of 2 pi by d. Conversely, any reciprocal lattice vector K has a family of real space planes normal to it, separated by destined V. So K is equal to 2. I am trying to tell you that in real space, crystal lattice, unit cell content and crystal structure and in real space, and in the reciprocal space you get xy primes who represents the unit vectors there. So my aim was to tell you that shorter distances, interplanar spacings will be larger. Shorter in the real will be larger in the reciprocal, and larger in the reciprocal means shorter in the real. So they will be reciprocated. And if I am telling you again and again that we have a diffraction pattern like this, then why are we not having peaks here? Because the material passes, the machine passes through that angle, but when it reaches here, it suddenly starts dropping down and go like this, and then started to jump. Why? So why the interference is becoming destructive? सोचो that the X-ray is scanning the whole sample. It gives us a peak here, then comes down here, then gives us a peak here. So what happens in between? This is important to know.